So, good afternoon, everyone. So, what did we discuss in our last lecture? What are the things we discussed in our last lecture? Do you remember? Hmm? So, we completed the proof for UCB regret, where we discussed that in the UCB regret, we have derived two bonds. One was an instance dependent bond, the other one was an instance independent bond. What was the instant dependent bond we got for UCB regret? Like we had something like this, right? Right? This is the kind of bond we got. And for instance independent, what did we get? Right? These are the bonds we got, right? So if you look at the instance dependent bond, uh, it is not easy to understand that we'll have an instance independent bond, right? Because as delta A tends to zero, it was going to infinity, right? In the instant dependent bond, as delta A goes to zero, it was giving us infinity as an upper bound. But how did we deal with this problem? Because for some, if I take delta A close to zero, then that was going to infinity, right? So how did we deal with this problem to get the instant independent bond? Because the second bond is applicable even when delta is going to zero, right? What did we do? So the intuition is that if delta is very low, then the contribution from that regret will be low, right? Because at most it can give you delta into t, right? If delta is very low, delta into t will also be very low, because so you segregate all the arms into two categories: the arms which have some delta threshold less than delta threshold and greater than delta threshold. If and the total regret from all the arms which have less than delta threshold will be delta threshold into t, right? So we have chosen delta threshold carefully in such a way that the overall regret is like this. So the idea was to mainly categorize them into two sets of arms, and then you analyze this separately. For the larger delta case, delta into t will not give you a good bond, so you use log t by delta bond for that. Okay, right. That is roughly what we discussed in the last lecture. And after that, what did we do? After the UCP regret analysis, what did we do? We were interested in proving some lower bonds on regret. So for that, we looked at some probability tools which are useful for lower bound. What are some lower bound? What are some techniques or tools we learned from probability theory? KL divergence. What does KL divergence mean? Like what is the formula? KL divergence of two distributions P comma Q is right. So is it a symmetric bound? Is it a symmetric function? So for example, for Gaussian, it could be symmetric. For Bernoulli, it could be asymmetric. And in general, it's an asymmetric. And what other properties do we know about this? It's always positive. And for Gaussian case, let's say you have Gaussian mu1 comma 1 and another Gaussian mu2 comma 1. What is the KL divergence? Mu2 minus mu1 whole square by 2 that we have seen. Right? And then what did we see? So what is the BH inequality? What does it tell us? If you have two distributions P and Q, the probability of A with respect to P plus the probability of A complement with respect to Q is always greater than or equal to KL of P comma Q. This is what for any event A, right? This is what we have seen. And what did we do after this? We have seen this inequality. So what is the use of this inequality? Like how did we use this inequality? We use this inequality to understand something, right? Do you remember what was that? Yeah, we looked at a problem called hypothesis testing, where you are given, let's say you have two distributions, let's say n of mu comma, like we used it in hypothesis testing. So let's say you have some two distributions, n of mu comma 1 and n of mu plus delta comma 1. And you are given some set of some t samples from one of these distributions. You don't know from which distribution those samples came from. Your task is to find out whether those samples belong to the first distribution or the second distribution. So what did we do by using the BH inequality? We defined an A, which is like the mean of the samples is greater than T by 2. If the mean of the samples is greater than mu plus delta by 2, then we conclude that the samples come from the second distribution. If the mean of the samples was less than mu plus delta by 2, we would have concluded that the samples came from the first distribution. So if we define A as the event where my samples are greater than mu plus delta by 2, that's a bad event for the first distribution. And A complement will be a bad event for the second distribution. So then we define A in such A like that and then use the BH inequality, right? So we were able to show that if if delta is less than 1 by root t, if delta is less than 1 by root t, with a uh, constant probability, we could be wrong. Our hypothesis prediction could go wrong with a probability which does not decrease with t. Like with a constant probability, we could be wrong. If delta is less than, then our prediction probability doesn't go to 0 with t. As t increases, our probability will not go to 0. That means there is a constant probability, irrespective of how large your t is. With a constant probability, you can make a prediction mistake, right? So this is a quick recap of whatever we have done in our last lecture. So in today's lecture, what we'll do is we'll formally define what do we mean by a lower bound of on regret, right? We'll define, there is a notion called min-max lower bound. Min-max lower bound definition. This is what we'll see. We'll see this min-max lower bound definition, and then we'll prove that the regret is expected regret will be so these are the two things which we'll do in today's class. We'll define what is called lower bound on a regret, and then we'll show that the regret lower bound will be of this particular form. Okay. Yes. Yes, constant. So that you'll understand when I discuss the min-max lower bound definition, you'll understand the impact of that. Okay. So just so our expected regret of any problem will depend on what all things. If I like the regret will depend on the time horizon t, and it will depend on what algorithm we are using, right? And it will also depend on what else, what environment we have, right? The true means and how many of them, the true means, right? So the regret will depend on t, the algorithm which we are using, and the environment in which we are operating, right? So the min-max lower bound tells the following is, so if you want to understand the performance of some algorithm, let's say I write that roughly like this, let's say I want to understand the performance of an algorithm, okay? Then what will be a reasonable way to measure the performance of an algorithm? If I want to say that my algorithm will not do bad than this, what will be a reasonable way? I can do this, right? Right? My algorithm performance will vary based on my environment. So for some environments, it might do well. For some environments, it might do bad. So if I want to talk about the performance of an algorithm, I should talk about the worst case performance. This is one way of dealing with it, right? For some environments, it will do good. For some environments, it might do bad. But if I am saying my algorithm is good, I should be able to tell that across all the environments, right? To just get a feel of this. So let's say I have an array like this of, let's say, some n positive numbers, n positive real numbers. And let's say the task is to find whether a particular number 10 is there in this array or not. Okay. So what if I ask you what is the complexity of this task? I have an array of n numbers, and I want to find whether a particular number 10 is there in this array or not. What will you say is the complexity of this algorithm? Like what any algorithm should have at least what complexity? N, right? We'll agree that we should have a complexity of n, time complexity of n. Answer. Yeah. So, but it does not mean that this algorithm will always take n time complexity, right? But still, you are writing it as greater than or equal to 10. What does that mean? Let's say in my array, the first element itself is 10. Then after checking the first element itself, I will be able to know that whether the 10 is there in that or not. So when I say that my worst case complexity of A is, and that doesn't mean for every instance of A, my algorithm will need n time complexity, right? So when you're talking about the performance of an algorithm, you should talk about for any input, my algorithm will not take more than this. Right? That's how we talk, right? So if I propose an algorithm from first to last, and when you say you find 10, you quit. So then when I talk about the performance of this algorithm, I'll say it's at least 10. I mean the worst case performance is n, because I can keep the 10 at the last position also for some a. So that's why what we are generally interested in is the worst case performance. So for example, any algorithm, if I keep all the mu's true means to be 1, then whatever any algorithm will have 0 regret, right? If I keep all the true means to be the same across all the arms, whatever algorithm you play, you will have 0 regret, right? So that means that's not the way to characterize the performance, right? When you're talking about an algorithm, you look at the performance of the algorithm across all possible environments, and the worst case environment, you look at for that particular algorithm, what is the worst case environment, you look at the performance of the algorithm in that environment, right? For example, if I say go, then let's talk about the worst case a. What is the worst case? Then so that is n. So this is how I define the performance of an should I keep this thing? So if this is how we talk about, yes. Yeah, this is it. We take looking at expected regret on. Okay. So this is about a particular algorithm, right? This is the performance of a particular algorithm. Now, if I want to claim that no algorithm can do better than something, right? When I'm talking about lower bound, what am I talking about? I'm talking about any algorithm will incur at least this much regret. That's what I mean when I mean lower bound. No algorithm can have a regret which is lesser than 8. That's what I'm going to argue. So what does that mean? So what is that I have to show if I want to argue like that? That no algorithm can incur a regret less than this. So this is what I should show, right? Min over all algorithms. Min over all like every algorithm has some performance. Every algorithm has some regret, right? Every algorithm has some regret. So even if you look at the algorithm which has the minimum regret, even that algorithm will incur this much regret. So it's min over algorithm, maths over environment, expected. Everyone is comfortable with this definition. So we are saying that there is no algorithm whose performance, whose regret can be lower than root kt. That's what we are going to prove. So this is what we'll be interested in proving. Okay. So for every algorithm, there will be at least one environment for which the regret is this much. Roughly, that's what it means, right? You take whatever algorithm you want. I will give you an environment in which the regret will be at least this much. Like this is like there exists an environment. You can think of this like there exists an environment for all algorithms. For all algorithms, there exists at least one environment in which the regret will be at least that, right? Because every algorithm might do well on some environments. So if my algorithm is always pick the first term and play it forever, even that algorithm will have 0 regret in some environments, right? If the first term itself is the best term in my environment, then even that blind algorithm will incur zero regret. So if I come up with another algorithm, say you always pick the second algorithm, you always pick the second now. Even that will do well on a lot of environments, right? So if I come up, so so for every algorithm, it will do well on some problems, but the performance will be measured based on how well it performs on the maths overall. Then, okay. So this is the definition of min maths bound. So how we prove it, we'll see. So as I told in yesterday's class, without going into proper technical details, roughly you can think of it like this. Let's say our environment has, like this is not a proper proof. I'm just giving you an idea where the root t comes from. So let's say I have some, so let's say I have some arms like this, like, let's say I have some, uh, and let's say there is another arm, let's say some mu2 comma 1, which is like, let's say greater than delta. Let's say mu plus 10 delta or something. Okay. Uh, so what do we know? Like, even after having t samples, totally how many trails we have? We have only t. So if I set my delta like 1 by root t, or if I set my delta as 1 by root t, so how many ever samples I take, because I have only t samples totally. So even after exhausting all the t samples, there is still a constant probability of not being able to identify which is the best term. Correct? So if you want to properly identify the best term, it's not possible within t samples. If you will not be able to distinguish two arms which are closer by less than 1 by root t within t samples. So other samples, other arms, you might be able to separate them out from the best arm. Like if mu of some, if the delta is greater than 1 by root t, you can separate them. With the, as t increases, the probability might go to 0. But for all the arms whose deltas are less than 1 by root t, it's not possible within t samples. So we might have to give up on them and say, okay, I might confuse them with the best term, and I might have to incur this much regret from them. So it's like 1 by root t into t, you will have a root t kind of a factor that's coming in. Hmm. Hmm. If I'm increasing t, when I increase my t, I'll change my environment also, right? For every, I'll keep decreasing my delta also. For every t, I'll show you some environment. For a given t and given algorithm, I'll show you one environment where it will do badly. That's all you want, right? No, you can't identify a good term across all the environments. Like you, like this is the worst case bound, right? So I'm talking about that. You change t, but I will give you an, I'm the adversary here. I'll give you the environment in which you'll do bad. You fix your t, whatever you want. You fix your t and come to me. I'll give you an environment in which you'll do bad. That means the worst case performance of that algorithm will be bad, right? So this is a rough intuition. Don't get carried away with this, but this, it makes sense, right? To take maths over environments. Just like how I said, any algorithm will do better on some environments. Always blindly pick the first term will do better on a lot of environments, right? So this is kind of worst case analysis in the sense that across any environment, my algorithm, what is the performance? Okay. No, we are saying that no algorithm can do better than this, right? So every algorithm has some performance. So what is the least regret that any algorithm can incur? So this is the regret that particular algorithm can. This is the regret that one particular. I'm asking what is the least regret that any algorithm can incur. So I'm just minimizing it over all algorithms. No, you can choose whatever you want, right? You want this is across all delta, right? What do you mean by, let's say this is my environment. My environments are coming from this set where, like this is one particular, for every value of delta, I have a different environment, right? So when I say that my algorithm is good, what should I say? My algorithm is good for all the environments. So I can take a max over delta, right? For every algorithm, you have for every delta, your algorithm will give a different performance. I will take a max over delta because that's like max over all the environments. So even then, whether your algorithm is doing good or not. Now, if I show you one environment in which your algorithm is bad, that means your performance of your algorithm is bad, right? So I'm just constructing a adversarial environment where I'm picking the delta which for which your algorithm will do bad. This is what we do. We show that no matter what algorithm you consider, I will give you an environment in which it will do badly. Like that's the point. We are not analyzing the performance of one particular algorithm. No matter what algorithm you come up with, I will give you one delta. I'll give you an environment in which the regret will be this much. That means there exists no algorithm which can incur lesser regret than this. So let's say you talk about this is one environment. So if I call this as one environment which has two arms, when I vary delta between across all delta, every delta is one environment. So it's like the performance of, let's say, of some algorithm on this environment will depend on delta, right? So I'll call this R T algorithm and delta, the performance. Now maths over all environment means maths over delta. Yeah. The maximum regret that particular algorithm will incur on any environment. What? Uh-huh. Yeah. Yeah, that's why I told it's a rough argument. I'll give the proper proof now. Yeah. That's not the valid proof, but that's the intuition on where root t term is coming from. Okay. I will tell that. So, as one of the students correctly pointed out, we are not having samples from one particular arm. We are playing the algorithm. We are deciding what samples we want to choose, right? At every time step, we are deciding what sample to choose. We are not forced to choose all samples from one particular arm. I can choose which arm sample I want to pick. But still, in that case, we will have to show that. Okay. So now, what are the samples that you see? Like, let's say any algorithm will start with some like a of one is the so what the construction of the proof is roughly going to be this, like let's start with the proof. It says that what I'll show is I will construct two environments as follows. The first environment, let's say, is n delta 1. Let's say it has two arms. Arm 1 has this is arm 1 has n delta 1. Arm 2 has let's say n01. So this is my first environment. I'm going to create one more environment, which is in which the first term will have n of delta 1, the same distribution as the first environment. But I'll create the second arm to be like this. Okay. Now I have two environments. The first environment is this. The second environment is that where in each environment there are only two arms. Okay. Now, as delta, like if you look at these two environments, what is the best term in first environment? This is the best term, right? And what is the best term here? The second term, right? Delta is some number. Delta is some positive number. It's a Gaussian distribution. So what is n mu sigma means? Yeah, n mu sigma means mu is the expected value. Yeah. So this is the reward distributions, like, and the best term in the this is the worst term, right, for this environment. So we have constructed two environments where the best term in the first environment is the worst term in the second environment, right? Everyone is clear with that? So now what we are going to show is, you pick whatever algorithm you want. I will show that at least in one of these two environments it will do badly. So if it does well on the first environment, then it is going to do bad on the second environment. If it is going to do well on the second environment, it's going to do bad on the first environment. That's the proof strategy which we are going to follow. Irrespective of what algorithm you come up with, you play on these two environments. At least in one of these two environments, you are going to have a bad regret. At least root k regret. Okay. At least in one of these two environments, your regret will be root t. That's what we are going to show. Okay. So the idea is the following. So as delta keeps getting smaller and smaller, as delta gets smaller and smaller, it is very tough to distinguish these two environments, right? Let's say as delta is going small and small, as delta is becoming small and small, those two environments will look almost like the same, correct? Because as delta tends to 0, environment 1 is equal to environment 2, right? So if you keep decreasing your delta, for an algorithm, it is very tough to understand whether it is playing in environment 1 or playing in environment 2. Because the samples will look more or less the same. As delta keeps decreasing, as delta tends to 0, the algorithm will very high likely get confused between whether it is playing in first environment or whether it is playing in the second environment. So roughly, it will play the same kind of arms in both the environments. So what will happen is, if the algorithm plays both, then the result in this environment will be good, and the result is bad. If the algorithm plays more, then the environment is bad. So what we're doing is, we're creating two very confusing environments and saying that whatever the algorithm will do, because it's very tough to distinguish these two environments, because as delta keeps getting smaller and smaller, like delta is like a 1 by root t kind of setting. It's very tough to distinguish these distributions from those distributions. So your algorithm will more or less play the same kind of samples in both the environments. So if it does well on this, it will do bad on this. If it does well on this, it will do bad on this. So that's the high level intuition. So let's make it more formal now. Okay. So Okay, so this is the intuition. So let's write the proof formally. So if we want to, so what we are trying to say is both the environments, if any algorithm that is playing, whether it plays on environment 1 or environment 2, it is likely to see similar samples is what we are saying, right? So what? So when you play your algorithm on one of the environments, so what is that you get to see? You will know what is the first term it has picked, then you will know what is the immediate reward it got, and then you will know what is the second term it picked, what is the immediate reward it got. So these are the this is the trajectory of a particular algorithm, right? Like whenever it plays on some environment, you will know this. It will have a sequence of the actions and the rewards, right? So now, if so, the probability of seeing, let's say you have some algorithm, and it is playing on environment 1. What is the probability of seeing this particular sequence? If I ask you that question, so you are playing on environment 1, and you are playing with some algorithm. So what is the probability of seeing this particular sequence? If I want to understand that, what will it look like? So it will depend on both the algorithm and the environment. So define the, let me use this notation. I will use pi to denote algorithm, and I'll just write V1 for environment 1 and V2 for environment 2. Okay. Now I want to understand what is the probability when I'm playing an algorithm pi on some environment V1. Sorry. What is the probability of seeing this particular, what is the probability of seeing this particular sequence? So it's like you decide an algorithm, and you, let's say, play on the first environment. You run your program till all the time slots are over. And now you're asking what is the probability that you'll see this particular set of sequence. Now, similarly, we'll have something for the second, right? And now we want to understand if whether the samples that you get when you played on environment 1, how close are they to samples that you get when you play on environment 2? So if you play on environment 1, you will get some sequence of samples. If you play on environment 2, you will get some other sequence of samples. Now we are asking, what is the uh, how what is the difference between these samples in terms of probabilities? Like you will have some distribution when you play with V1, you will have another distribution on the set of samples that you see when you play on V2. Now we want to understand how close these two samples will look like. So we're asking how close these two distributions will look like. So what do we do? What distance metric we know, like what measures we know? KL divergence is one such thing. So now we want to understand what uh, what is the difference between these two okay. If this is very low, that means if the KL divergence between these two distributions is very low, that means you are very likely to see same sequence of samples, whether you play on environment 1 or environment, right? As delta equal to 0, then the probability P pi V1 will be equal to the probability distribution P pi V2, right? If delta equal to 0. Because if delta equal to 0, then V1 is equal to V2. So you'll have the same. But delta is not equal to 0, it is some other number. So then in that case, what is the how how much is the difference between the kind of samples that we see when we play on environment 1 and what kind of samples we see when you play environment 2, that we can measure using the KL divergence. So this is like in last class we have seen, right, when you have T samples from a KL divergence, like when we have T samples from some Gaussian distribution, how can we get the KL divergence for PT? Like if P is the distribution of each sample, how did we get the KL divergence over PT? KL divergence between PT and QT? Because these are independent samples, you remember when we are getting KL divergence between PT comma QT, we just use the additive property over KL divergence because the samples are independent. So we were able to write KL PT QT equal to sigma over like T into KL PQ, right? Does everyone remember when we had T samples? Like we had something like this, then we wrote this as K into something like this, right? So similar thing will be applicable here, but here we don't know how many times we played arm one, how many times we played arm two. Like we had two arms, right? So what it will depend on is it's a result which we can use. What it will depend on is, so how many times you played arm one into the KL divergence between arm one in environment one versus arm one in environment two. How many, like it's like this, like expected NT of arm one. How many times you played arm one is this, right? What will it depend on? It will depend both on the environment and, yeah. So what we'll write is expected over, it will depend on environment and algorithm of arm A into the KL divergence between the first arm in environment 1 versus the first arm in environment 2. Okay. So I'll write like this: the number of times you played arm 1 into KL divergence between n of what was the first term in environment 1? N of delta comma 1 comma n of 0 comma 1. Okay, plus, so this is nothing but you have to sum over all the KL divergences. We are just summing over how many times that particular arm has been played. What is the second arm in first environment? N of delta 1 only, right? Is this clear to everyone? Huh? Yeah, this is the first. This is the first term. Okay. Okay. So how many times you played arm 1 into the difference between the first and second. Like how many times you played arm? The difference between the first environment and second environment. Then how many other times you played arm 2 into the difference between the second arm of the first environment and the second arm of the second environment. No, we will call them arm 1 and arm 2. We can call them with some index. Yeah, there will be reverse, but we are fixing some order right. Sorry, it's V1 only. Thanks. Okay, is this clear? So this is just like the yesterday's concept where we are just summing over how many are times. Like here, what is that we are trying to find the difference between that and find the difference between this and this. Like that is one quantity. And difference between this and this is another quantity. So how many times this difference will be counted? How many ever times you played arm one? How many times you found this? How many ever times we played arm two? So that's all I'm writing here. Yeah, it will differ. Like it's a KL divergence, it's not symmetric, right? So this is if I write this here and this here, because of because of this. Okay, like like here it's not straightforward. It's a theorem which you have to prove, but we are not proving that. It's a result. It's not straightforward. Okay, it's intuitive. Like it's intuitive to explain, but it requires a rigorous proof. Okay, this is a fact. You can take it as a fact. Okay. So now the question is whether we are able to differentiate between the environment one and environment two. That's the question, right? So that depends on the KL divergence between these two distributions. Now, what is it we want to prove? We want to prove that the regret in at least one of these two environments is bad, right? So we want to use the BH inequality to do that. Okay. So if you want to use the BH inequality, to argue something like that. Can you tell me one bad event in environment one? What will be a bad event in environment one? Arm two is played, let's say, more than t by two times. That's a bad event, right? In environment one, playing arm two more than t by two times is a bad event because you are playing a bad arm more number of times than the good arm. And a complement is a like bad event in the second case, right? So for first three examples, they second term more times than bad. For the second and first term more times than bad, right? No, A is this thing. So you are like this is sample space which we are in. Hmm. That's a bad event in environment too. Hmm. No, that's second. No, we are talking about this sample. Like, if this is the set of samples that you see, like let's say you played an algorithm and these are the samples which you got. So what is a bad event for in this sample space for you? Like playing ARM2 more is a bad event for first environment. Playing ARM2 more is a bad event for the second environment. So that's but the sample space is same, right? The sample space is this, which is how many times you played ARM1. No, we'll write we'll condition on it. I'm just talking about event. I'm not talking about the probability, right? It's like this. See here, when I say so when I talk about A complement, I'll measure the distribution with respect to environment 2. Right now, I'm just talking about a particular set. Okay. So, but when I write the probability, I'll write P of A, which is like P pi V1 of A. When I write Q of A complement, I'll write P pi V2 of A complement. Okay. So now we'll try to define an event A like this, which is playing arm1 more than, or I'll write like this. Okay, so and A complement is correct. So this is a bad event for environment 1. This is a bad event for, this is a good event or bad event? Huh? Okay. So then I'll change this. Okay. Now what is that I want to do? I want to use the BH inequality. What will it say? Probability of when you play some using some algorithm pi on environment 1, what is the probability of A? Okay. Plus when you are playing algorithm 1 on some environment V2, what is the probability of A complement? This is P Q is greater than or equal to half times exponential of KL divergence of P pi V1 comma P pi V2. Right? This is from BH inequality. So here what we are trying to say is whatever algorithm you come up with, there will be some uh, constant probability of playing bad even. Okay. So what this will be equal to? This this term will be equal to what? Half times h of what is the KL divergence between pi P pi V1 and P pi V2? If you see this term is not KL, right? Why? Because the mean difference is 0. So only the second term contributes. So which is like minus expected NT of A2 into how much? So what was difference? The difference was 2 delta, right? So it's like 2 delta whole square by 2, which is 2 into delta square. Correct? So now we'll so what do we know about this thing? What is the expected What is the, can we give a lower bound for this? I want to remove the expectation and NT, all that. Is there any trivial lower bound that you can give for this? Minus T into 2 delta square. Correct? Because, yeah, and it's a decreasing function. Right? So this is at least greater than or equal to this much. Since, okay. So now if I choose my favorite thing, delta equal to 1 by root T, what will I get? 1 by root T or 1 by T root 2, something I'll choose. Or even before going there, maybe let's keep it like this. So for a moment. So this is what we got. We'll call this one, but this is not what we are interested in, right? We are not interested in how many times we are playing the bad arm. What is the main? We want the regret, right? So how do we compute the regret? Can we write the regret in terms of this? Can we get a lower bound on the regret in terms of this? This is what in example form you are playing arm A, arm A1. Sorry, you are playing arm A1 at least or less than or equal to T by 2 times. That means our regret is at least how much? So whenever you play arm A1, or whenever, that means you're playing arm 2 more than T by 2 times, right? So whenever you play arm 2 in the first environment, we are incurring a regret of delta. Correct? What is our second? Like whenever you play a second arm in our first environment, we are incurring a regret of delta. So the event A means we are playing the second arm at least T by 2 times. So the expected regret will be at least T by 2 into delta. Whenever that particular event happens, it will be at least greater than or equal to delta into T by 2. So we can argue that the expected regret in environment 1 so the expected for any algorithm is greater than or equal to delta into T by 2 into probability of, is it correct? Everyone is clear with it? The expected regret, the first environment, whenever this particular event you are in the you are playing the arm to more than T by 2 times. So whenever you play arm to more than T by 2 times, so whenever so when this event doesn't happen, also you will incur some regret. We are interested in only lower bound, so we are just writing this. If you want to do it properly, we should have written plus the expected regret given A complement into probability of A complement, right? The expected regret will be the expected regret given A complement. That's the expected regret given A complement. Correct? No, A complement while it is, let's, if you want to write it properly, I'll write it like this. Expected RT V1 phi given A into probable phi V1 of A plus expected regret right? This is just a condition. Like this we have been doing before. Right from the first class we are doing, like you are defining some event as good or bad. Now you are saying expected result is expected result given event, event with expected result in bad event in a problem of bad event. So this we have been doing always. So now what do we know this? The first term, whenever the event A happens, what is the bound on expected regret? When event A happens, what happens? We play arm2 more than t by 2 times. So the expected regret in the when we condition on A, which will be delta into t by 2, at least that much. Uh, at least that much, right? Because whenever the event A happens, we are playing arm2 more than t by 2 times. So whenever you play arm2, you are getting a regret of delta, right? So at least this much into probability of A plus something. This will also contribute to some regret, but their interval will be lower bound. So I'm just writing it like this, okay? A plus something, okay? Which is positive because the regret will never be negative. So it's a positive thing which I'm neglecting because I'm interested in the lower bound. Is everyone clear with this? All the time thinking you want the expected result and just conditioning on the result and that conditioning. Similarly, what do we know? Expected R T V2 pi is greater than or equal to what? So whenever event A happens, it's a good event for the second case. So we'll not worry about that. Good event will not worry. We were in the bad event, A complement is a bad event. So whenever A complement happens, how much regret are we having? 2 delta, right? Delta or 2 delta? Delta. Yeah. So because the best term has 2 delta, the second best term has delta. So we are incurring a regret of delta whenever you play arm 1. So the A complement means you are playing arm 1 more number of times. So that means you have delta into t by 2 into probability of, right? This is the same logic, whatever we did before. So now from if I use if I call this as 2, now from 1 and 2, what can we say? Like that was our 1, which was saying that the probability of A, the first and the second element is greater than or equal to something. Now can I write, now I know how to write expected regret in terms of A. So what is expected regret in terms of A and A complement? Expected regret. This is the expected regret in the first environment plus expected regret in the second environment. The expected regret in the first environment plus expected regret in the second environment is greater than or equal to what? From equation 2, what can we say? Sorry. Delta t by 2 into correct from 2, from 1 and 2, or just from 2. From 2 we get this, right? 1 I'll use now. I haven't used 1 now till now. So I call this as 1. Okay. Everyone is fine till now. Now we will use the BH inequality. Like from 1 we get what? We get this is greater than or equal to t by 2 into half into a, what was that? Half into h power minus 2t delta square. Correct? Till now I haven't made any assumption on what my algorithm is, right? So now this the sum of two numbers is greater than or equal to something is, what can I say about the maths? Before that, I'll just choose my delta. I can choose whatever environment I want because I'm talking about the worst case environment. So if I choose delta, if we choose delta equal to, if we choose delta equal to 1 by 2 root t, what will I get? I'll get this to be greater than or equal to, am I missing something? I am getting delta from t. Okay, so what will I get? Did I miss any half or something somewhere? No. So what will I get here if I substitute this delta? Huh? Root t by 8 into h power minus 2 t into 1 by 4 t, which is like minus half, right? So this implies that maths over expected regret in t v1 pi comma expected, because maths is greater than or equal to sum by 2, we'll just use that, is greater than or equal to root t by 16 into h power minus 1 by 2. Okay. Yeah, so that's all. We got root t. Okay. We are able to show that for any algorithm, we'll be able to, for any algorithm, there is at least one environment in which the regret is root t, c root t. Okay. So in particular, for two Gaussian distributions, we showed that one environment will be from these two environments. Okay. We just need to show one environment in which the regret will be at least this much for any algorithm. Whatever algorithm you take, you play on these two environments. In at least one of these two environments, uh, your regret will be at least c root t. Okay. Yeah. So this is a little bit involved, but I hope I have explained you the key concepts in a decent way. So maybe when you go back and read it or watch the recorded lecture again, you will understand it better. Okay. Maybe I'll give you one exercise also where you can apply this concept on a different problem, and then you will understand how to use this. Okay. Like first time it will look a little bit overwhelming, but this is some kind of techniques which you'll use in multiple places. Like let's say you are doing some research on some bandits. So this is a standard trick which you will use everywhere. So you have to understand what is your problem and how you can apply this technique in your problem. Okay. So for example, this proof, if you understand it carefully, we can show that instead of taking the infimum over all algorithms, instead of taking the min over all algorithms, if I take min over all ETC algorithms, min over all explore commit algorithms, like min over all explore commit algorithms means min over all possible m's. Like m is the only parameter in our explore commit algorithm, right? So if I do that, I can show that the lower bound will be t power 2 by 3. So any ETC algorithm, you give me any ETC algorithm, I'll give you one environment in which the regret will be at least c into t power 2 by 3. Okay. So this is, that is, we restricted the minimum over only ETC algorithm. That's why you are getting t power 2 by 3. Here we are allowing all possible algorithms, so the minimum will still decrease, right? So that's an exercise which you can try it out. I'll maybe release it in the problem set weeks. But roughly you understood the proof, right? So it's about roughly we are saying that we'll construct two environments which will look very similar. So any algorithm you give, any algorithm, it is very tough for an algorithm to distinguish these two environments because the delta is chosen such that the samples from the first environment will look similar, very similar to the samples from the second environment. So there is a good chance of getting confused as to which environment it is in. So if it is not able to differentiate between these two environments, it can do only good in one of them, right? If it does good on one, the other environment, the performance will be bad. So you're making these two environments so close that the samples will look same. So the algorithm will behave in the same way. But if it behaves in the same way, it is going to do bad in at least one of these. So that's the very high level idea. And this is the formal proof. So I understand it will take a little bit of effort to go through the details, but I recommend you to read it and watch the lecture again. You will be able to understand. Okay. But if delta is very less than 1 by root 3, then the regret itself is low. Like, let's say delta equal to 0. There is no regret with this sentence. So it's a sweet spot. Like you are trying to pick adversarial delta. Like if delta is very large, then it can easily differentiate these two arms and these two environments. If the delta is very small, then also it can, there is no regret at all. Delta is very small, you won't incur any regret. But you are keeping some delta where the regret is significant enough, but small enough so that the environments are confusing enough. So it's like you are making delta small enough to look to both environments the same, but the regret is significant enough